A mathematical model of transistor currents. Ibis-Moll model, edit. The DC emitter and collector currents in active mode are well modeled by an approximation to the Ibis-Moll model. 3 lines. Line 1, I sub cap E equals I sub S times open parent E raised to the fraction with numerator V sub B and denominator V sub cap T power minus 1 close parent. Line 2, I sub cap C equals alpha sub cap F I sub cap E. Line 3, I sub cap B equals open parent 1 minus alpha sub cap F close parent times I sub cap E. The base internal current is mainly by diffusion, see Fick's law, and J sub n of open parent base close parent equals 1 over WQ D sub n sub B over V raised to the fraction with numerator V sub EB and denominator V sub cap T power, where 1 V sub cap T is the thermal voltage, kT divided by Q, approximately 26 MV at 300 K, almost equal to room temperature. 2. I sub cap E is the emitter current. 3. I sub cap C is the collector current. 4. Alpha sub cap F is the common base forward short circuit current gain, 0.98 to 0.998. 5. I sub S is the reverse saturation current of the base emitter diode, on the order of 10 to 10 amperes. 6. V sub B is the base emitter voltage. 7. D sub n is the diffusion constant for electrons in the p-type base. 8. W is the base width. The alpha and forward beta parameters are as described previously. A reverse beta is sometimes included in the model. The unapproximated Ibis-Moll equations used to describe the 3 currents in any operating region are given below. These equations are based on the transport model for a bipolar junction transistor. 3 lines. Line 1, I sub cap C equals I sub cap S times open bracket open parent E raised to the fraction with numerator V sub B and denominator V sub cap T power minus E raised to the fraction with numerator V sub BC and denominator V sub cap T power close parent minus the fraction with numerator 1 and denominator beta sub cap R times open parent E raised to the fraction with numerator V sub BC and denominator V sub cap T power minus 1 close parent close bracket. Line 2, I sub cap B equals I sub cap S times open bracket the fraction with numerator 1 and denominator beta sub cap F times open parent E raised to the fraction with numerator V sub B and denominator V sub cap T power minus 1 close parent plus the fraction with numerator 1 and denominator beta sub cap R times open parent E raised to the fraction with numerator V sub BC and denominator V sub cap T power minus 1 close parent close bracket. Line 3, I sub cap E equals I sub cap S times open bracket open parent E raised to the fraction with numerator V sub B and denominator V sub cap T power minus E raised to the fraction with numerator V sub BC and denominator V sub cap T power close parent plus the fraction with numerator 1 and denominator beta sub cap F times open parent E raised to the fraction with numerator V sub B and denominator V sub cap T power minus 1 close parent close bracket, where 1 I sub cap C is the collector current. 2 I sub cap B is the base current. 3 I sub cap E is the emitter current. 4 beta sub cap F is the forward common emitter current gain, 20 to 500. 5 beta sub cap R is the reverse common emitter current gain, 0 to 20. 6 I sub cap S is the reverse saturation current, on the order of 10 to 10 amperes. 7 V sub cap T is the thermal voltage, approximately 26 MV at 300 K, almost equal to room temperature. 8. V sub B is the base emitter voltage. 9. V sub BC is the base collector voltage. Base width modulation, edit. Main article, early effect. As the collector base voltage, V sub CB equals V sub CE minus V sub B. Varies, the collector base depletion region varies in size. An increase in the collector base voltage, for example, causes a greater reverse bias across the collector base junction, increasing the collector base depletion region width, and decreasing the width of the base. This variation in base width often is called the early effect after its discoverer James M. Early. Narrowing of the base width has two consequences. 1. There is a lesser chance for recombination within the smaller base region. 2. The charge gradient is increased across the base, and consequently, the current of minority carriers injected across the emitter junction increases. Both factors increase the collector or output current of the transistor in response to an increase in the collector base voltage. Punch through, edit. When the base collector voltage reaches a certain, device-specific, value, the base collector depletion region boundary meets the base emitter depletion region boundary. When in this state the transistor effectively has no base, the device thus loses all gain when in this state. Gummel-Poon charge control model, edit. The Gummel-Poon model is a detailed charge-controlled model of BJT dynamics, which has been adopted and elaborated by others to explain transistor dynamics in greater detail than the terminal-based models typically do. This model also includes the dependence of transistor beta values upon the direct current levels in the transistor, which are assumed current independent in the Abasmol model. Small signal models, edit. Hybrid pi model, edit. Main article, Hybrid pi model. The hybrid pi model is a popular circuit model used for analyzing the small signal and AC behavior of bipolar junction and field effect transistors. Sometimes it is also called Giacoletto model because it was introduced by L.J. Giacoletto in 1969. The model can be quite accurate for low-frequency circuits and can easily be adapted for higher-frequency circuits with the addition of appropriate inter-electrode capacitances and other parasitic elements. H-parameter model, edit. Another model commonly used to analyze BJT circuits is the H-parameter model, also known as the hybrid equivalent model, closely related to the hybrid pi model and the Y-parameter two-port, but using input current and output voltage as independent variables, rather than input and output voltages. This two-port network is particularly suited to BJTs as it lends itself easily to the analysis of circuit behavior, and may be used to develop further accurate models. As shown, the term X in the model represents a different BJT lead depending on the topology used. For common emitter mode, the various symbols take on the specific values as 1 terminal 1, base, 2 terminal 2, collector, 3 terminal 3, common, emitter, giving X to B, 4 2, base current, IB, 5 IO, collector current, IC, 6 VIN, base to emitter voltage, VBE, 7 VO, collector to emitter voltage, VCE, and the H parameters are given by 1 Hx equals high for the common emitter configuration, the input impedance of the transistor, corresponding to the base resistance P. 2 HRX equals HRE, a reverse transfer relationship. It represents the dependence of the transistor's input, IBVBE curve on the value of output, VCE. It is usually very small and is often neglected, assumed to be zero, at DC. 3HFX equals HFE, the forward current gain of the transistor, sometimes written H21. This parameter, with lowercase fe to imply small signal, AC, gain, or more often with capital letters for Fe, specified as HFE, to mean the large signal or DC current gain, DC or often simply beta, is one of the main parameters in datasheets, and may be given for a typical collector current and voltage or plotted as a function of collector current. See below. 4 Hox equals 1/Ho, the output impedance of transistor. The parameter Ho usually corresponds to the output admittance of the bipolar transistor and has to be inverted to convert it to an impedance. As shown, the H parameters have lowercase subscripts and hence signify AC conditions or analyses. For DC conditions they are specified in uppercase. For the CE topology, an approximate H parameter model is commonly used which further simplifies the circuit analysis. For this the Ho and HRE parameters are neglected, that is, they are set to infinity and 0, respectively. The H parameter model as shown is suited to low frequency, small signal analysis. For high-frequency analyses the inter-electrode capacitances that are important at high frequencies must be added. Etymology of HFE, edit. The H refers to its being an H parameter, a set of parameters named for their origin in a hybrid equivalent circuit model, see above. As with all H parameters, the choice of lowercase or capitals for the letters that follow the H is significant. Lowercase signifies small signal parameters, that is, the slope, the particular relationship. Uppercase letters imply large signal or DC values, the ratio of the voltages or currents. In the case of the very often used HFE, 1F is from forward current amplification, also called the current gain. 2E refers to the transistor operating in a common emitter, CE, configuration. So HFE, or HFE, refers to the total DC collector current divided by the base current, and is dimensionless. It is a parameter that varies somewhat with collector current, but is often approximated as a constant. It is normally specified at a typical collector current and voltage, or graphed as a function of collector current. Had capital letters not been used in the subscript, i.e. if it were written HFE, the parameter indicates small signal, AC, current gain, i.e. the slope of the collector current versus base current graph at a given point, which is often close to the HFE value unless the test frequency is high. Industry models, edit. This section needs expansion. You can help by adding to it. January 2015. The Gummel-Poon SPICE model is often used, but it suffers from several limitations. For instance, reverse breakdown of the base emitter diode is not captured by the SGP, SPICE Gummel-Poon model, neither are thermal effects, self-heating, or quasi-saturation. These have been addressed in various more advanced models which either focus on specific cases of application, Mextram, HICM, modular, or are designed for universal usage, VIC. Applications, edit. The BJT remains a device that excels in some applications, such as discrete circuit design, due to the very wide selection of BJT types available, and because of its high transconductance and output resistance compared to MOSFETs. The BJT is also the choice for demanding analog circuits, especially for very high-frequency applications, such as radio frequency circuits for wireless systems. High-speed digital logic, edit. Emitter-coupled logic, ECL, use BJTs. Bipolar transistors can be combined with MOSFETs in an integrated circuit by using a BiCMOS process of wafer fabrication to create circuits that take advantage of the application strengths of both types of transistor. Amplifiers, edit. Main article, electronic amplifier. The transistor parameters alpha and beta characterize the current gain of the BJT. It is this gain that allows BJTs to be used as the building blocks of electronic amplifiers. The three main BJT amplifier topologies are 1 common emitter, 2 common base, 3 common collector. Temperature sensors, edit. Main article, silicon bandgap temperature sensor. Because of the known temperature and current dependence of the forward-biased base emitter junction voltage, the BJT can be used to measure temperature by subtracting two voltages at two different bias currents in a known ratio. Logarithmic converters, edit. Because base emitter voltage varies as the logarithm of the base emitter and collector emitter currents, a BJT can also be used to compute logarithms and antilogarithms. A diode can also perform these nonlinear functions, but the transistor provides more circuit flexibility. Avalanche pulse generators, edit. Transistors may be deliberately made with a lower collector to emitter breakdown voltage than the collector to base breakdown voltage. If the emitter-base junction is reverse biased, the collector-emitter voltage may be maintained at a voltage just below breakdown. As soon as the base voltage is allowed to rise, and current flows, avalanche occurs and impact ionization in the collector base depletion region rapidly floods the base with carriers and turns the transistor fully on. So long as the pulses are short enough and infrequent enough that the device is not damaged, this effect can be used to create very sharp falling edges. Special avalanche transistor devices are made for this application. Vulnerabilities, edit. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. June 2023, learn how and when to remove this message. Exposure of the transistor to ionizing radiation causes radiation damage. Radiation causes a buildup of defects in the base region that act as recombination centers. The resulting reduction in minority carrier lifetime causes gradual loss of gain of the transistor. Transistors have maximum ratings, including power ratings, essentially limited by self-heating, maximum collector and base currents, both continuous forward/DC ratings and peak and breakdown voltage ratings, beyond which the device may fail or at least perform badly. In addition to normal breakdown ratings of the device, power BJTs are subject to a failure mode called secondary breakdown, in which excessive current and normal imperfections in the silicon die cause portions of the silicon inside the device to become disproportionately hotter than the others. The electrical resistivity of doped silicon, like other semiconductors, has a negative temperature coefficient, meaning that it conducts more current at higher temperatures. Thus, the hottest part of the die conducts the most current, causing its conductivity to increase, which then causes it to become progressively hotter again, until the device fails internally. The thermal runaway process associated with secondary breakdown, once triggered, occurs almost instantly and may catastrophically damage the transistor package. If the emitter-base junction is reverse biased into avalanche or Zener mode and charge flows for a short period of time, the current gain of the BJT may be permanently degraded, as the emitter is smaller than the collector and cannot dissipate significant power. This is a common ESD failure mechanism in low-voltage devices. See also, edit. 1 bipolar transistor biasing. 2 Gummel plot. 3 insulated gate bipolar transistor. 4 multiple emitter transistor. Notes, edit.